our first keynote speaker is Ulrich Heinen from Bruker Biospin.
Ulrich. Yeah.
The computer switch itself off. Take it away.
Sadece bana yakın ol da bir sıkıntı olursa sen zaten başlı başına bir sıkıntısın. Alınma, tamam mı? Şaka yap. Kaydediyorsan.
Okay, good morning everybody, and thank you Emily for the kind invitation. It's certainly a great honor for me and my colleagues to be allowed to give a keynote speech here, so thank you very much for that. I'd like to start off where I finished 2 years ago in a keynote in Berkeley. This was my final slide back then. We were on the edge of getting our standard working by that time, but I had no chance other than talking about the future those days, the future of BI. Today, I would rather talk about the presence of MPI, because the news from our side from last year is that we actually were shipping the first machines. And you can see here the UK in Hamburg, University Clinical Hospital in Eppendorf was installed in June, and in December at the Charité in Berlin. So we have the first machines out there. This talk will not be strictly a scientific talk. I leave that to my younger colleagues. I thought it might be interesting for you to hear a bit about the background of such a development of the story behind such a machine. I mean, if you buy a coffee machine from some vendor, you're probably sure that they have solved all the problems in delivering you a perfect coffee and there's nothing to do about it. But we all know that MPI is still a very hot stuff, it's a new technology. And I don't want to pretend that we have solved all the open questions in MPI. We hope that we can deliver a tool that we all together can work together with to bring MPI forward. And that's really the story behind the talk today. Although I'm talking about the presence of MPI, we should not forget what the next step should be. In my opinion, the next big step that is coming forward is, of course, the move to bring MPI to the clinical domain, up to humans. And one of the questions today is the machine can help on the way. There's a difference between clinical and preclinical world, of course. If you look at small animals, we are working with small field of views. We can work with old-sized animals and can accept long acquisition times. And with another safe operation because the field limits are quite high, so quite complexity there. Whereas for humans, we of course have to cover larger field of views. We have to keep the acquisition times down to acceptable times for comfort of the patients. Of course, as Emily was most prominent to work out, we have to deal with PNS limits as also the Philips groups demonstrated. And of course, there are the SAR issues. But I feel we can use today's preclinical machines to pave the way for clinical imaging later on, and to develop techniques to deal with these issues. So what kind of people might be using preclinical MPI machines? And I tried to recognize some groups of key scientists that might be interested in preclinical imaging. From my point of view, these are the early adopters among the radiologists. Those who want to experiment with a new modality, knowing that it's still a large uncharted waters that remains to be explored. So you may want to work out MPI application protocols. Which amount of contrast agent to use, how fast to inject multiple times at once, so lots of open questions. We want to compare MPI to other modalities. What specific advantages might MPI have for diagnostic purposes? And what specific imaging problems we might be able to solve? Of course, we might be interested in diagnostic intervention imaging, because a large area of application has been proposed in that area. Then we have the MPI fundamental researchers. Those might be interested in sequence design for MPI experiments. We might have people interested in reconstruction techniques. The barrier of entry to MPI field was always the problem that you have to build your machine so far. So having a machine available might help more people to enter the field and do their own studies in reconstruction and sequence design. And finally, there's a large group of scientists who are working on new particles and exploring all the options that new particles, tailored particles, labeled particles we give, and then to try out the performance of the particles under real imaging conditions. So these are, from my point of view, the group of key scientists that may want to work with preclinical MPI machines. Okay, if you plan to go to the market and develop an MPI machine, you have a certain number of challenges to face. One area is, of course, the contrast agents. There are so many different contrast agents available already, engineered in different groups, and they have different properties. So, what is the contrast agent that you want to design your scanner for? There are certain interdependencies. So, at some point, you have to decide on the specs of your machine and hope that it will work with a large range of particles. Then, of course, you have to deal with the high scientific expectations. MPI has very, very many promises, and they're very well justified from a theoretical point of view. And I think in particular, the Philips group has actually shown, has done pioneering work for many of these applications. But still, you have to say that many things have only been tested superficially. And, there's a lot of work to do to show that MPI can really do these things in depth. Secondly, we are comparing to many other well-established technologies which have 30 to 40 or even more years of background and are very, very well developed. And of course, the MPI was still, well, at the beginning, so it's not as straight as the well-established technologies yet. And then there are, of course, issues of the technology. For MPI, we're using simultaneous acquisition and detection, which is a challenge. We have high requirements in the transmit system for linearity and spectral purity to be able to actually detect an MPI signal. And of course, there's the issue of rapid progress of technology. That's what we're all sitting together here with many smart people coming up with new ideas. So the typical turnover of the commercial development is a bit longer than if you just try out things in the laboratory. You have to make sure that when you come to the market, your product isn't just outdated. So it's good to have some way to keep your development aligned with what's going on in the community. Okay, most important point probably is that they have a large number of diverging scanner designs. I mean, we all have been very creative in coming up with new ways of doing MPI. So imagine you're a young scientist in a company and you're assigned the task, tell me what the best MPI scanner design is, and then look what is available. We have the field 3 points there. I'm trying to create a map of what's available. It might be incomplete by now, or by the end of this conference. But generally, we have FFP scanners, we have FFL scanners, which can again be distinguished in those working with magnetically rotated field line, those with mechanically rotated object. For the FFP scanners, we have those with 1D excitation systems and shift coils. With excitation system, I'm referring to the coils operating in a resonant circuit in the sinusoidal frequency, whereas the shift coils will be operating in a stepwise manner at typically low frequencies. You can have the same thing. They work based on the Cartesian trajectory, as we learned yesterday as well. You can do the same thing with 2D excitation systems and shift coils. We can have 3D excitation. That was the first mouse scanner published by Philips in 2009. We could extend these 3D excitation systems, which work along this Lisa trajectory by shift coils. Comes later on, sorry for my thought. If we want to even go further, we can find some very specific implementations of the 1D scanners. For example, the single-sided scanners. I hope I got that right, Xenia. The traveling wave MPI has got a very clever design from Würzburg, which also has a 1D direction of the field 3 point and slower direction in the reverse things. I hope I got that right again. Then the 3D scanners can be equipped with shift coils, and they all have been hybrid systems derived from the 3D systems and the traveling wave systems. So it's a rather complex chart. If you want to characterize these scanners, you could think about properties like speed, resolution, field of view, sensitivity, flexibility, and so on. On the drawback side, the complexity, the technical complexity, the size, or the infrastructure requirements that these machines take. All these different scanners have different virtues on their own. So, which one should you build for in vivo imaging if you want to go to market? Well, we have to decide the answer to the question at some point. We know that the high resolution MPI data, fast MPI in vivo, has been published mostly from the 3D excitation scanners at the time when we started. And this seems to be one of the more versatile concepts for now. And so our scanner is located here, 3D excitation plus shift coils. And you may note that if you have such a machine, you're also covering the other cases here. So in case you didn't make the right decision, you have at least covered a large range of the field here. So we think you end up with a rather versatile system here. Okay, how do we come to the machine? I've shown the slide 2 years ago already. We had a very fruitful and happy collaboration with Philips. And so there's an ancestry in the preclinical demonstrator built at Philips, where we used, where we learned the MPI technology and combined it with our expertise on preclinical MRI imaging. So we did an integrative redesign to come up with our machine, the Bruker preclinical MPI system. So its ancestors are the preclinical demonstrator developed by Philips, and of course the MRI scanners for which we use a large amount of hardware and software. Okay, how does such a typical industrial development process look like? There are many steps. I've actually not included all of them on the slide here. First, you have to come up with a system specification. What do you want to do? You have to specify all the components that will make up the scanner. We'll go into that in more detail in a moment. You have to develop all the components that you need for your machine. You have to integrate them so to make sure that they all play smoothly together. You have to prepare everything for production, from a regular production line. You have to produce all parts in the end. You have to deliver and install them. And that includes things like packaging and loading of lorries and so on. In the end, you have to support your customers. I mean, this is, from my point of view, part of the entire development cycle here. And then parallel to all of this, you have to do the risk analysis. I've deliberately drawn the arrow of the entire screen because it really accompanies the entire process here at every stage. And of course, you have to document very well what you're doing, show the machine in the end. To dwell a little further on the risk analysis, just to give you an insight into that, you have to analyze your entire system on component level, on system level. You have to study the delivery process. Could a huge magnet tip over and knock out someone's feet, for example? You have to worry about the installation process when the whole system is not enclosed and maybe the dangerous vault is open. You have to discuss service operations, how we can handle the machine safely in case of a service. You have to discuss regular operation. Is there any risk for the operators? Risk for the people, risk for the equipment, and of course, risk that you might get wrong data from the machine. It's also a risk to discuss. If you're unlucky, you can build your risk analysis on actual experience. If you're lucky, you have no such data because nothing happened during the process, then you just have to have a perverse fantasy and come up with all horror stories what could go wrong with the machine. And the task is really then to have come up with a design where your machine, where each of these horror stories will fail to miss the happy end in the end. So in other words, you have to make sure that each horror story ends happily in the end. When you get a working machine, no risk with people. Wait. And then you have to design measures for risk mitigation, how you can solve this. It's an iterative process that accompanies the entire development. Fortunately, there are software tools available where you can track all your work and check whether you've done all the right things and that you haven't forgotten anything. Okay, the first task during development is really to come up with the system design and to split the machine into components. If you have the entire MPI system here, I think splitting up the front end, the back end, and some support infrastructure, then you can refine it further. Is it? Come on. Doesn't like me. Here we go. The front end can be split into magnet system, resonant circuits, preamplifiers, calibration, road, and enclosure. The enclosure is not quite unimportant because it saves you from hitting dangerous parts. The back end can be separated into power management, digital control, transmit part, receive part, that's amplifiers. Your support infrastructure includes a Faraday cage, a cooling system, lots of cables, and a power distributor. And if you want to refine it further, your magnet system might be the drive field, the selection field, and shift coils, focus field coils. The same splitting occurs for the amplifiers here. Your Faraday cage can be separated further down in the actual cage and filter plates, which you cannot purchase anywhere. The cooling might include oil and water, and so you can work down to the component level. The key here is if you do the componentization right, you can deal with the challenge of advanced technology. Because the design is sufficiently modular, you can upgrade the components as you learn how to do better and better and better as the technology evolves. Now, once you have accomplished this task, you have to worry where to get the components from. So, think of any scanner component. You could decide either to use the unmodified Philips technology, just build it ourselves, replicate it. In many cases, we chose to introduce certain changes, to re-engineer things, and develop and produce it at Bruker. Some cases, we actually find that we can use stock components that we have been using for ages at Bruker. In some cases, you might decide it's not really your business to build a cooling system, for example. There are companies that can build excellent chillers, so you just buy them. And in some cases, you have to actually ask a different company to produce the things as you would like to have them, because they have the facilities to do so. Just to give you one example here, what this decision process might be, let's think about the drive field. We can ask whether a 25 kilohertz drive field is actually more suited to an RF coil or grading system, if you only are familiar with MRI technology. So what could be for the points on either side? Is it like an RF coil? Well, it's a resonant transmit receive system like an RF coil. So that's a point for RF technology. And it's operated in AC or low frequency mode, like the RF coils. And the other might be more like a gradient system. It's operated at extremely high powers in kilowatt regime. And you need active cooling, which is a technology on its own. So at that point we decided, okay, our drive coil is more like a gradient system. And we set up development production of this drive coil in our gradient group, which is located in Visomur in France. On the other hand, all the technology of getting the signal into the coils is really a bit like RF technology. So the development of all the transmit chain was allocated to our RF group in Switzerland, near Zurich, in Verlanden. And that way you have to find out where to use things and where the right technology is located. Second example, the input for your drive amplifier. Where can you get it from? You could think, well, do you use something similar to an RF channel? In Bruker terminal is a frequency controller and a signal generation unit, which has exceptionally high time resolution of 12.5 nanoseconds. There's a very sophisticated RF switching technology, which you don't really need for MPI. And then as just one output per channel. Well, maybe that's a bit too much specs for us. And then gradient systems operating with a time resolution of 1 to 8 microseconds. That sounds better for us. It's the right amount of data we can process here. We can have actually 16 channels per unit here. We have real-time channel mixing that is possible via the digital pre-emphasis processing unit. And we have a very high precision, it's very stabilized analog output. So in our case, we decided this is the way to go to actually generate the signals for our drive system. This is just one example with many of such decisions on the way for building such a system. Now, when you start your component development process, work on specifications for each component, you develop them, you test them, you integrate them, and then you give feedback to the developers, and you might start the cycle maybe a second time again until everything fits well together. And there's a lot of paperwork along the way, of course. Specification sheets, and for each thing you need large lists of components. This is taken from our SAP data sheet for one of the cabinets. I think the first 2 levels of hierarchy have already 300 parts that have to be maintained and stocked and so on, and built together along according to the specifications. And you have to draw a lot of cables, cable plans, and develop special cables here. You have a lot of charts for that. It's a lot of work until you can actually replicate it to the machine in the end. Just to give you a little insight what's happening behind the scenes here. Okay, while all the component development is in process, you have to prepare your own site. So draw a chart of your laboratory where to place everything, purchase a Faraday cage and get it installed, so when the scanner is ready, you have a place where you can actually test it. You have to purchase a lot of measurement equipment which you might not own to start with. You have to build your own calibration tools, some things you just cannot buy anywhere, so you can build yourself, both hardware and software. And you have to prepare the software integration, which is one of the next few slides that I come to. Of course, when then at some point all the equipment arrives, all the components are ready, the first thing to do is not start an experiment, although you might want to make sure that you're safe when you're doing all that. Check that the system shuts down properly when it gets getting too hot. Make sure that it shuts down if you have a loss of fluid flow. Make sure that it shuts down when the supervision system actually has a flaw itself. Make sure that all the thresholds are on the safe side. Check the acoustic emissions. We actually check that we have no ultrasound emissions from our scanner, which you might worry about when you're working with 25 kilohertz with quite high powers. You have to do a high voltage isolation test to make sure that you cannot harm yourself. And you have to test the calibration or it doesn't squeeze off your fingers at some point. So only when you've done all that, you may actually start the interesting work. Well, that takes a lot of time. Because if you're looking at your spectra on a logarithmic scale to get the high sensitivity, you only see your biggest problem. So if you test your components one after another and you find out you have a problem somewhere, the spectra don't look nice, and you find fiddling around with one component doesn't change anything, doesn't mean the component is good. It just means that something else is worse. So you have to continuously review all parts of the hardware over and over again until you solve all these issues. And you have to keep close contact with the development production all the time to feed back all the experience you gain over time. And during the whole time process, you have to establish all the part lists, cable plans, manufacturing instructions, all that. Again, a lot of paperwork. Okay, when the software, actually, when you may have prepared it very well, but when you first bring it together with the hardware, it won't fly all over your face probably. Because getting your established software working together with a completely new machine is a challenge. So initially, you have many interrelated problems, and you have to find your way through it. Maybe you have to do workarounds until you get the initial work done. And at some point, everything will fall into its place. Okay, to quote Bernhard Gleiche, I think I couldn't say better than that. The best precondition for building a decent MPI system, decent MPI scanner, is having a decent scanner already, because then you can test components in a working system. So at some point, you have to get the process done. Thanks for allowing me to quote you on that. Okay, turning to the software. Our software package PowerVision was initially an MRI only software package. So we somehow had to train it to cope with MPI. So we integrated the new version that came out in December 2013, but we started actually a lot earlier to train it to MPI. What challenges might you have? First of all, MPI needs to become familiar with the new hardware that we're going to use. And there were a lot of assumptions wired in the software. That we have the RF system all the time. Then we have a nucleus to discuss or to define the frequency. We have a grading system. So you have to tell the software, you don't care, this all doesn't matter anymore. We are doing MPI, not MRI. And actually some of the embedded devices in the machine had to be trained for the MPI mode as well. And you have to establish the acquisition framework. Of course, the reconstruction framework to be a stop was very fundamental for this work, and they actually got the reconstruction working in our package here. And at some point, you have a working software package for MPI, studying the dual modality software. Well, after many months of work, at some point you get the first image. Here's one of our first images. We have a phantom here with 9 cavities filled with resolvist. And if you look at the image that you can get from that, fits very nicely. So what you do when you have done that, of course, have a party. You've done lots of hard work, and you deserve to celebrate a little bit. But then you have to do something else that is very interesting. Tell everybody you're not finished yet. Make it clear that you cannot do joint in vivo measurements tomorrow. Make clear that you cannot install the machine your customers will board you tomorrow. That's still many months off. Because the expectations will be very high at this point. So, what is still remains to be done? We have to continue to improve all components and optimize integration. We have to prepare the manufacturer documentation further and to establish the test instructions. We have to check and optimize the workflow for the user. We actually have to change that rather late in the process because we found out we had conceived or designed at the beginning didn't really work out very well, so we changed that rather late. We have to do the end user documentation. We have to hunt down the number of software bugs. Actually, we ship our software with a source code for the high-level layer so that people can design their own sequence. So you have to polish up your source code and you can actually show it to people and explain how it works. You have to test the first applications. You have to verify the specifications that you start the process with. You have to verify the machine stability. You have to train your colleagues who will operate the machine. You have to support marketing and sales who can come up with procedures. So you have a nice lady coming to your laboratory and doing a photograph in front of the machine. If you're wondering why she's not wearing safety goggles here, that's because the contrast agent in question here is coffee. Just in case you wonder. We didn't actually take a spectrum of that. Okay, you have to define the service stuff that you might need if there's a problem in the field that you have to repair, when you have to repair something. But it can be actually a rather costly thing. Okay, and one certain issue all the time is comparability of application data. Because if you change a machine every day, it means it's quite difficult to compare an image you did last week with an image you did this week. So it is certainly an issue to have this stability in your own doing all this time. Well, at some point you can make an official statement of what they've achieved, and this I've taken out of some of our brochures with Paravision 3 MPI technology, Paravision 6 software, 3D imaging, all that. You can read it yourself. You can nail down the specifications that you want to publish, stated here. And again, I want to point out this very fruitful collaboration with Philips, which has helped us come to this state here. Okay. To show you some images finally. Here's an image of a phantom. Actually, these images were not on our own machine. These were taken during the installation at the Charité in Berlin, during the final test there. Here's a resolution phantom. Looks like this. On the poster outside, if you want to take a closer look. We have a grid of contrast agent dots here. The largest gaps are 3.5 millimeters. The smaller ones here just 1 millimeter apart. This is 1.5 millimeter. Quite surprisingly, although this is the weak gradient direction, this is 1.25 Tesla per meter, we can almost resolve even the 1 millimeter gap here. Quite surprising. This is our field of view, and total position was just 2.2 seconds. So we were quite happy with that. Another end, you might want to take the speed of your machine. So we took a little dot of contrast agent for microliters of reservoist and moved it through the field of view with our calibration robot. Just 2 millimoles of iron actually, and it's 22 milliseconds per frame, getting a nice movie shaped half speed here. Same field of view, and the entire sequence only spans 650 milliseconds. So that also seems to work quite well. Okay, then we might start in vivo applications. These are the data, the settings we used for the experiment for RAT, and pick out one frequency of the entire spectrum. In the end, you can see very nicely that with a short bolus injection here, after some seconds, with the question yesterday how long it takes. In this case, 1.5 seconds later, you see the contrast agent appearing in the heart region here. You see the heartbeat superimposed. Quite nice, actually. And if you turn that into a movie, with the MRI background, still image behind, you have a slice in the MRI data set and the max intensity projection of the MPI data superimposed. 3 different views here. Well, it seems to work. But of course, we were happy when we reached that state. Okay, then maybe it's time to go to the customer's laboratory. Here's some photos of our first installation in Hamburg. We found a beautiful empty fire cage installed machine. We crowded into one office with all sorts of hardware. This is about half of what we shipped. The rest was in the scanner room already, all packaged nicely up and stored there. And then it took some time to cable it all together and screw it all together. You see it's working here until the machine was fully completed. Then in the end, we had a nice machine standing there. Of course, even during the installation, you're learning a lot of things, because working in a foreign laboratory with the tools that you have in your car is quite different from working in your own laboratory with lots of helpful colleagues around. You build the components. There you're on your own. Lessons learned: double check all your cable lengths that you've taken with you. The laboratory might be larger than it looked on the papers, and suddenly you find that one cable is 10 centimeters too short. So we order a longer one from home. Second thing is, there might be other people working there, so you might reshuffle your installation procedure. So you have to be rather flexible to get the machine working there, or deviate from your plans. Okay, in the end, when you're done, you have to keep close contact with the system users. You can learn a large number of things from them. It's extremely helpful to stay in close contact with them. You want to help them to realize their ideas. Sometimes you feel that you've maybe omitted something and you have to dress up your software to cover something else that they find useful. It's a very, very great thing you can advance if you use this proper tool. And we actually do visit them regularly to check that everything is working, get experience how the machine performs under the user's hands. And I think this is the point where I really have to say a huge thanks to the people involved. And just to name a few, I would like to acknowledge Professor Gerhard Adam, Michael Kaul, who's in the audience, Tobias Knopp, and Olaf Kosch from the P2B, Harald Kratz, Tobias Mummert, Jörg Schnorr, just alphabetical order, in particular over here. It has been really, really enjoyable to work together with you. Moreover, if I look back to my first slide, I can say that here, just a few selected people here actually cover the three groups of people that are identified early on, which machine is targeted to. So we can say really the machine is in the right hands now, which I'm very happy with. Now, to see where we are today, now I've shown this chart earlier, 2 years earlier, and maybe at the end of conference I will learn that it's outdated already, which machines are installed right now. The blue ones here are the Bruker machines. Still, it's very much a Germany-based scale. If we had the strong US output in California, the map will get more diverse. And maybe I've actually forgotten a few systems, so let me know if I missed you here. Just to say, we have 3 further deliveries planned for this year, but certainly one message is that we need definitely more MPI systems outside Germany. I think we showed it very clearly as well. So that's something we really aim at. Okay, we did all the work in Ettling with a core team located here, shown here. Many more people in other Bruker companies and other sites. We have Jochen Franke here, who's a PhD student who spent most of his time on the MPI MRI hybrid system. He has really worked out lots of the hardware technology improvements, which will fold back into our commercial development. So he's done a great job in hardware integration testing. To put to the point, I think Jochen is the one who strives to build the perfect MPI system on the board here. On the other hand, there's Alexander Reber, also a PhD student, who's interested in all the things that the MPI systems are not perfect. So I think the two are competing. One is each one is trying to make the other one work less. Jochen builds the perfect system, so there's no imperfections to correct. And Jochen says, oh, well, you don't need a perfect system because I can compensate for all of that. So quite nice to have such smart people around. In the side from Hofsky, who did really a terrific job in the first installations, and was essential in really getting everything ready for delivery and production. Heinen is invaluable for integration testing. He's very good questioning us whether we did the right job, and was essential in the hardware integration testing, and also did most of the installation in Berlin together with Ralf Dombrowski. Myself, I've been doing the who's next? Nicoletta is next. She's been covering all the NPS measurements. We've done a lot of tests of materials and of contrast agents. And she's also getting into the MRI and PI application support. Myself, doing the odd bits that remained to be done, mostly software hardware integration, and it was also part of installation, test, and service. Well, we're with some other colleagues at 4 different other Bruker sites, which designed the components, which we have a close and frequent collaboration with. And one item of news here is that we're looking for someone else to join our team of field application scientists. The position will be hopefully be open sometime this year. So if you're interested in doing integration and testing work and supporting customers, well, contact us in the coffee break later on. Okay, what are we interested at Bruker? We're not doing fundamental API research, to be honest. We're interested in getting the technology better and building better and better systems. So on the product, we're doing system design, manufacturing, research. We are looking to optimize the construction algorithms, application research, and want to combine the BI with other imaging modalities. We have our MPS spectrometer, which we use a lot in-house for testing all the materials that are used for building the commercial product, but we also test a lot of third-party contrast agents on most of Nicoletta's work, really. And then, of course, we have the big machine, the hybrid system, which is an ongoing design study. working with the same quality as for the preclinical system, but we do not maintain all the part lists to the user. We accept certain inconveniences in the workflow operating that, because it's really not planned to be a product at this stage. So it's a terrific machine. You will hear more about that from Jochen later on in this morning. We're also using it to test new components that we want to introduce. Okay, so altogether, we're doing technology-oriented research here, and just to sum up what fell out of this work during the last year, IWMPIs, some contributions that we made. This year, we're talking about first phantom measurements. Well, you see the talks during the conference here. Okay. Altogether, could say that we want to contribute to a bright future of MPI. We want to continuously improve the hardware and software, refine the workflows for animal handling acquisition and construction. We want to evaluate more applications and provide predefined protocols. And we have many other ideas, so stay tuned for next year's IWMPI. Okay. To summarize, turning a completely new imaging modality such as MPI into an end-user product is certainly a major effort. But Bruker is now ready to deliver such scanners that actually do allow serious experimental work. And I would like to refer to the talks of Michael Kaul and Tobias Klopp in the conference, which shows some of the initial work done with the installed scanner there. Well, now for something completely different. Those who know me like that I enjoy finishing on a light note. Maybe light note is the right thing to know. You may notice that this lecture hall beautiful Istanbul is called the Fazıl Say Hall. You know, Fazıl Say is one of the most distinguished artists of Turkey, a world-class pianist and distinguished composer. So let's talk about music. I've been always intrigued by the relationship between MPI and music, because it was Bernard Kleist's ingenious idea that the generation of harmonics by the nonlinear properties of particles allows to do synthesis acquisition and detection. Well, the generation of harmonics is the very process that gives musical instruments the correct sound. We have the flute, the trumpet, violin, the oboe playing a B flat. It's all the same frequency, but they sound very different because they are the harmonic spectra. And you can tell them apart. Now, if a particles also generate harmonics, you may wonder, what if the particles were a musical instrument? What would they sound like? I wanted to find out, and what I wanted to find out on real data. So I took that little movie of the particles sweeping across a field of view, and sampled it down by a factor of 100. So our frame rate drops from 46 frames per second to 1 frame every 2.2 seconds, and our frequency changes from 25 kilohertz to 250 hertz. For the musicians, that is B in the third octave. If that's B in the third octave, the third harmonic is F sharp in the fifth octave. You will following audio clip will hear this distinct hum of the F sharp, or check with the piano actually, of residual third harmonic, which is a direct feed through from the transmission system, unsuppressed residual third harmonic. But then the particles appear on stage, as you saw in the movie already. So please enjoy the sound of MPI. Does it play? Can you hear? No. Wait. That's bad. It worked well, we tried it out. On? Yeah, come out.
Could you take it up?
So we tried out before.
Evet, başka bir prensesini gösterecekti de ama her zaman
Well, this was meant to be a compliment to the sound and vision session of the IWM, but we have the technical problems here, I'm afraid. So let's just look at the spectra, which have the conflict here as a replacement for the sound. Maybe we can show it later on. What you see here, if particle sweep in, you see the spectrum appearing here, and you can see that even with these 2 millimoles of resonance field, still 6 or 9 cues about the voltage flow down here. So really good for the sound flow. Just looking forward to it all the week. How can we manage? Okay. Maybe have a second chance to present the coffee papers. Okay, now, so no sound today, but still want to thank you for listening patiently. And
I think we have one.
First we hear the sounds of the party.
very briefly, I was still kindly allowed to replay the movie that didn't work out earlier. I think now we have got the audio working, so what was missing earlier, please enjoy the sound of the piano. Let's have sharp background, sing the third harmonic, live and through.
Thank you very much for this nice demonstration.